Thank you. I'd like to talk today about the prospects for semiconductor qubits for quantum error correction. I'm from Silicon Quantum Computing at the University of New South Wales, where I work with Michelle Simmons, who I'm sure a lot of people here know. And I'd like to start with a quote from Richard Feynman, who said, "I'm not afraid to consider the final question as to whether ultimately, in the great future, we can arrange the atoms the way we want, the very atoms all the way down." And in Michelle Simmons's fabrication techniques, this is something that we're fast approaching being able to do. So in this talk, I'm going to give you some highlights of sort of recent progress, or maybe an introduction to the types of qubits that we're thinking about, some of the recent devices that you may or may not have seen. I guess if you're in Australia, you may have seen, but maybe some of the international visitors haven't seen so much. And then talk about the potential for scale-up. So the way that we could potentially reuse some of the control elements and the types of couplings that would allow us to scale from the smaller scale devices that we can build at the moment to a larger scale types of devices that we would want for quantum error correction and fault-tolerant quantum computing. So I guess this talk is all about going from the top picture there, these smaller scale devices, down to something where we might be able to do the surface code. So let me first of all introduce you to the types of qubits that we're talking about. We're talking about donor qubits in silicon. Specifically, we're talking about phosphorus donors. There's a schematic, there's a kind of a picture of the way that this works. You've got one single phosphorus atom inside a silicon lattice. Now, phosphorus has an extra electron. That's what makes it a donor. So of its 5 valence electrons, 4 of them form covalent bonds with the nearby silicon, and 1 is relatively free. And it forms basically a hydrogen-like wave function around the atom. And this gives us not one, but two qubits that we could use. There's an electron spin, so that's that extra electron spin. And there's also a nuclear spin, because phosphorus has a nuclear spin of 1/2, so there's a nuclear spin there. And we can address those with ESR for the electron, so microwave frequency pulses to control the electron spin, or NMR radio frequency pulses that we could use to control the nuclear spin. And of course, these two are coupled. There's a hyperfine interaction that couples between the electron spin and the nuclear spin, and that's rather a strong coupling, so it's about 100 megahertz or so. And so that electron spin and that nuclear spin, they're essentially always coupled. If you had more than one donor, then they would also couple. So there's an exchange interaction where if the wave function of your electron spins overlap, then you get an exchange interaction. And you can typically, that's quite a strong interaction, maybe gigahertz, and typically that is of length scales maybe 10 to 20 nanometers, something like that. Okay, so that's the basic qubit that we're talking about, where we've got a nuclear spin and an electron spin as our qubits. So why might you consider these types of qubits? Well, the first thing is that the decoherence rates for these qubits can be extremely long. So if we have isotopically pure silicon, then we can measure decoherence times on the order or greater than 30 seconds for an ionized nuclear spin, and greater than 1/2 second for the electron spin. And these are dephasing times with CPMG. And so, the ionized nuclear spin in particular has an extremely long dephasing time. So they make very good qubits. The other thing that people often think about when they're thinking about semiconductors is the potential to scale. And of course, we know that in conventional computing, this is exactly what's happened. We've gone from something like CIRAC, which was Australia's first computer there. It's an image from 1949, maybe looks like some of the labs today, down to silicon wafers, where we can regularly fit millions or even billions of bits. And we don't even think about that. And so the hope is that in semiconductor quantum computing, we can make use of a lot of the same techniques that we've used for conventional electronics and be able to scale. So if we think about the qubits now and some of the parameters that you might be interested in. So first of all, measurement. We can do measurement of these qubits with an Elzerman style readout, where you've got an SET, single electron transistor, there next to what is in this case 2 quantum dots, and you can basically have tunneling from the dots to the SET, and if that occurs, then you see current through it. So you arrange so that one of the spin orientations will tunnel and the other won't, and this allows you to read out your qubit. You can do quite fast readout. So, for example, if you in the paper on the left there, there's 1.5 microsecond time for the readout and 97% fidelity. Or on the right, we can go much slower, 99.9% fidelity readout with 13 millisecond readout time. So the one on the right there is a new technique where you ramp the voltage of the ramp the voltage as you're doing the readout, and you can read out in that way. If you're thinking about the fidelities, the gate fidelities for these qubits, so for the electron spin, it's been measured to be 99.94% fidelity for the single qubit gates. So, in that experiment, the typical gate times were around about 3 microseconds for a pi pulse. So that's all very good. How can we actually fabricate these types of devices? And this is what Michelle Simmons has been working on, and the amazing techniques that she has. So she has precision lithography using a scanning tunneling microscope. So you're probably aware of scanning tunneling microscopes, and typically used to image devices. Here we are going to use them to fabricate the device. So you start with a silicon surface. The grey there are the silicon atoms. What you do is that you can introduce hydrogen, and that terminates the surface. So you get a layer of hydrogen resist on the surface there. Using the tip of the scanning tunneling microscope, if you apply a large voltage, you can actually desorb some of that hydrogen from the surface in exactly the locations that you would like. So, sorry for the bad PowerPoint here. I can have a tip which desorbs some of the hydrogen from the surface and opens up a patch there of the silicon below the hydrogen there. When you introduce phosphine gas, more bad PowerPoint coming up, you can have it so some quite complex chemistry occurs, but the phosphorus from that phosphine gas can incorporate into the surface and actually kicks out one of the silicons. You could then grow over the top with silicon, and now your phosphorus has become incorporated inside the silicon lattice. And so in this way, you can build almost atomically precise qubits or wires or control structures all on that plane, and do that with almost atomic precision. You don't have quite atomic precision because you opened a patch and you're not sure exactly which lattice side the phosphorus donor went into, but pretty close. And finally, of course, we can then use conventional electronics with wire gates to connect down from the surface to those buried structures that you've fabricated. Okay, so some of the notable achievements, these are things you may well know about. Michelle and her team were able to fabricate a single atom transistor where the active element of this transistor was one single atom. So you've got a source and a drain lead there, and if you look carefully in the middle, there's one single phosphorus donor, and that's the active element of this transistor. So you can build a transistor that operates and has an active element of just one atom. Or on the left side, you can build a wire. They're building wires, and they showed that that had ohmic behavior all the way down, right the way down to that nanoscale. More recently, there's been experiments here. This is an example of a square root of swap gate. So we want to be able to interact two of the electron spins here together. So in this experiment, this was done in natural silicon, where they basically performed a 2-qubit gate, a square root of swap gate. They got a very fast gate time, so less than a nanosecond, and a fidelity of 94% for interacting their electron spins together and doing 2-qubit gate. And I guess most recently, we've been, or SQC has been trying to fabricate larger devices. So here's an example of that. These aren't qubit devices so much as a series of quantum dots. There's 10 quantum dots here that you can see going between the source and the drain. And what this device was meant to do, and in fact did, was to emulate the SSH model. So that's a topological model. It's got pairs of dots that are strongly coupled, then weakly coupled, strongly coupled, weakly coupled, all the way down those chains. And it matters whether you have the strong coupling first, or you have the weak coupling first. You get two very distinct phases. One, there's a topological phase. When you have the weak coupling first, then what you find is at the ends of this chain, that's where the electrons basically are localized, can be at the ends of this chain. Or if you have the trivial phase where you have the strong coupling first, then you find in the ground state that the electrons all the way across the chain. So you get two very different types of behavior from the topological phase or the trivial phase. And so in a real experiment, Michelle and her team were able to fabricate these dots, these 10 dots, and had then 6 gates around to control the voltages and control the parameters of these experiments. And because they had such exquisite control of exactly where they fabricated the dots, they were able to arrange to have exactly those couplings that I described and do a simulation of this model, actually building it in an experiment. Now, what you actually measure in this experiment is the current that goes from the source to the drain through those quantum dots. And you can work out, based on the energy levels and the states, when you expect to see current through these types of devices. And you see a very different signature when you've got the trivial phase or the topological phase. And they were able to measure those currents and show that they were getting what they expected for this model. So for the topological phase, you see just those 2 peaks there, whereas for the trivial phase, you see many peaks. One of the important things here is that, although you've got 10 dots, you're using only 6 gates to control that, and that's because of that ability to really fabricate these devices with exactly the parameters that you would like. So, of course, none of this is me. This is all experimental people, Michelle Simmons' team, and this is some of them. This is at SQC, and we find ourselves at the University of New South Wales. So what's the prospect then for scaling up these types of devices in order to be able to perform quantum error correction? There's been quite a number of different proposals for how to do this, and this is just some of them. I'm sure I've missed out some off the list here, but there's quite a large number, and most of them are going for the surface code, which I think is everybody's favorite code, or maybe not anymore. You can each one of these has different qubit types and different types of couplings that it's based on. So I thought I'd start with one that I helped work on, and that is this idea of having parallel use of the gates. So making use of the control wires that you use to control the quantum dots as much as possible. So one of the problems that you have with these types of devices, or the difficulties you have in when you're thinking about different architectures to go to error correction, is you've got both a blessing and a curse from the size of these devices. So it's a blessing in that you can build very small devices, but it's a curse in that you need to run in enough controls in order to control the devices that you've got. And so in this architecture, what we're trying to do is make the best use of our control elements. And those are those wires that you see running across the top of the chip and across the bottom of the chip. The idea here would be that we would reuse those wires for as much as we possibly could, so that we could get control of these devices. So you can see that each of those wires couples not to just one site, but to many sites, and that we could reuse them in that way. Most of the interesting action for this design actually would happen on the middle plane. Would happen there where we've got each one of those red dots, one of those qubits that we talked about, and they're all clustered around an SCT island. All of this would be put in a large magnetic field and could be controlled in the ways that we've been seeing before. The proposal was that most of the time the qubits would be ionized, and so there would be just nuclear spin qubits, and that would basically be your data qubits in your code. Right. And as you might remember, that's the state in which there's these very long decoherence times. And we had a proposal for how to do this. The basic idea was that if you wanted to perform an operation, you would tunnel an electron onto that particular site, do your operation, and then ionize the qubit again. So most of the qubits wouldn't feel this pulse because they're at a very different frequency, because without the electron, obviously you don't have a shift in the frequency because of the electron. Once you tunnel on the electron, you get a very large shift due to the hyperfine, and that allows you to target just that site or sites and not any of the other sites. If you wanted to do a 2-qubit gate, the idea would be that you could do this tunneling onto 2 sites, do, for example, a C0 between the nuclear spins via the electron spins using those NMR and ESR pulses. And we came up with pulse schemes that would do all that sort of thing. And I'm sure you can see how with that square array, we could implement the measurements that we would need in order to be able to do the surface code. So it would be a series of tunneling electrons onto these devices, performing the gates, and then ionizing again. And you would do that to measure each of the syndromes and extract those for the surface code. In fact, you could even think of the electron spins as something like flag qubits for a scheme like this. Now, this design we came up with it a while ago. It's really extremely technologically challenging, and some of those are being overcome, and some of them are still difficult, I guess. I should say also that there's another variation of this in which we use much stronger, much more closely spaced electrons, where we have an extra qubit in the middle, and that allows you to put your qubits closer together and get that really fast exchange interaction. One of the technological challenges was when we proposed this that it's obviously in 3D, it's on more than one plane, and at the time we proposed it, that hadn't been demonstrated. So here's an example from 2019 where we've got an SCT which is now built on 2 planes rather than just the one plane. So progress towards that. Now there's still things to do in order to, if you wanted to realize this, and it'll be exciting to see if those can be overcome. So let me also, so that's one way that we could potentially think about scaling up to a large scale architecture by reusing the controls as much as we possibly could in order to implement the surface code. There's also a number of other ways that we could get there, and a lot of them involve longer range couplings, and this allows you the space then to run in another control control gates in order to control your qubits. So we've been thinking mostly about the top three ways of coupling qubits so far. The hyperfine, that couples between your nucleus and your electron spins. Exchange, which would couple between your electron spins. And if you put your qubits slightly further apart, the wave functions no longer overlap. You still get a coupling, a magnetic dipole coupling between your electron spins. So all of these are relatively short-range couplings and mean that your qubits have to be close together. If we want to go to larger sizes, move towards fault-tolerant quantum computation, perhaps we should be considering longer-range couplings. So I'll talk about some of those now and some of the progress towards seeing those. So those are a charged dipole, which you could get from an EDSR-type qubit that I'll describe in a couple of slides. And in that case, the coupling between qubits could be as much as, say, 200 nanometers between your qubits. And you still get strong coupling. You could also think about shuttling electrons around, so moving an electron from site to site through several dots and move your electrons physically around. Or you can imagine coupling to superconducting resonators, and all of these would be paths towards much larger scale architectures that we might like to pursue. So the first of those is electron shuttling, and here what you're doing is that you've got several locations, several quantum dots, and you can imagine applying voltages to tunnel your electron from site to site and physically move your electron around in order to get longer range couplings between your qubits. So you could imagine doing this over the scale of tens of micrometers. So some of the examples in the literature, this is one thing which is being actively pursued by quantum dots. And on the left here is an example of such an experiment where they've got 5 quantum dots and they're tunneling an electron between each of those sites and backwards and forwards. And they're able to do this 250 times or so and tunnel over tens of micrometers. You can also imagine the way that this could scale up into an architecture. So on the right there's a proposal for doing exactly that type of thing, where you've got chains of these dots between each of your qubits in your surface code. And you can think about coupling by shuttling the electrons from site to site. But these techniques, they have their drawbacks. For example, they could be quite slow in comparison with the techniques that I'm about to tell you about. And of course, you've got to have that exact control to tunnel from site to site. So another way to get longer range couplings is through EDSR and flopping mode qubits. So EDSR is electrically driven spin resonance. And the easiest way I think to think about that is imagine that you've got two dots, 2 sites where your electron could be, and you apply voltage that shuttles or takes the electron from one site to the other. And if you imagine that you're the electron, you basically are moving with that. And if there was then a magnetic field gradient, what you would feel is an oscillating magnetic field as you go from site to site. And this is essentially the idea of electrically driven spin resonance. And you can drive then a transition between 2 of the energy levels using just the voltage control and not through a magnetic field. Specifically, I learned about this technique first from Andrea Ambarello, who had a proposal to drive not in a magnetic field, not in a magnetic field gradient, but between 2 sites, one of which had a hyperfine interaction and the other had none. And he was thinking specifically about a donor and the surface. So if you drive between the donor and the surface, on one site you've got the hyperfine interaction, on the other site you've got none. And the same principle is the same, but now the states that you're driving between are not spin up and spin down, but these states, which are combined states of the nuclear spin and the electron spin. So the electron spin up and nuclear spin down, or vice versa. And if you look at the Hamiltonian, in that subspace, basically we've got that Hamiltonian there, and the off-diagonal elements are just the hyperfine. So as we then electrically drive, we'll be driving a transition between these two states. And he and his co-workers were able to turn that into a type of architecture, and more recently demonstrate this in experiment. So that's those two papers down the bottom there. Now the great thing about these qubits is that, well, they basically spin, but when you work out the details, what you do is that you're living at that equal superposition point with at a superposition between each of the two sites, and this gives these types of qubits an electrical dipole character as well as that magnetic character. Not a very large one. It's a small effect, so that these states are ever so slightly dressed, but they do have that character, and that's what gives them ability to couple then over much larger distances, and potentially up to, as I said before, maybe a couple of 100 nanometers with gates in between them. The other thing that you might be able to do then also is to couple them to a resonator. So if you have a resonator nearby, before, when we had just a magnetic dipole, if we worked out the strength of coupling to the resonator, maybe to do a gate, that would be extremely slow, hertz, and way too slow to do any type of quantum computing. But with these electrically driven types of qubits, EDSR qubits, these flip-flop qubits as we call them, if you had the same thing, they would couple to that resonator, and you might be able to couple them over much, much larger distances through a superconducting resonator. And this is the idea of the Delft group down the bottom here in experiment, showing these types of qubits able to couple to a resonator over 250 micrometers. At one end, they've got a double quantum dot. At the other end, they've got a double quantum dot of the type that I've been describing. And they were able to couple and show coherent coupling over that resonator. So very, very much larger coupling, and much longer distance coupling. Now the fidelity of these devices, at least it's only a preprint so far, but the fidelity was much worse than you might want for quantum computing. And so there's a number of things that you can do to improve these, including working on the resonator and the coupling between these two, and designing your EDSR qubits so that they have much narrower line widths. And this is something that SQC has also been thinking about. We would like to be able to do this, but with these almost atomically precise fabrication techniques that we have. And so this was an idea by Felix Krauth, where he was thinking about doing this between two dots that are fabricated using these techniques. On one side, on the right side for you, that's basically your EDSR qubit. That's the one that's like the flip-flop qubit that we had before, where it's got the nuclear spin of that and the electron spin form your qubit. And then on the left, you have another site with two nuclei there, and that's the site that you can essentially tunnel to. And so you can drive between these two quantum dots and do a lot of the same operations. So this nuclear spin states would be electron spin up and nuclear spin down, and vice versa. Got the two sites, you can electrically drive between the two. So here's sort of the three different proposals, all very similar for these EDSR type of qubits. One between the donor and the surface, the other between two quantum dots in a magnetic field gradient, and the third one there with basically two quantum dots that are both fabricated. Now, when you think about these devices, one of the most important factors is the change in field in the Z direction, if you like, that you feel as you go from one site to another. Thanks. And why this is important is because you can imagine if there was some charge noise in your device, what would happen is if that affected your qubit and drove it onto one side or the other, you'd feel this change in essentially the magnetic field in the z direction, and that would lead to dephasing of your qubits. And so what you want to do is you want to arrange, if it's possible, you want to arrange to have that change in frequency to be as small as possible. And for the one on the right, what you can do is if you arrange for nuclear spins to be in opposite orientations, hopefully their contributions from their hyperfines would cancel themselves out, and you could get a very small gradient as you drive from the left to the right. And this would lead to, hopefully, to much longer decoherence times. And at least in theory, we could simulate this out and show that, at least in principle, we might be able to get quite good fidelities from these types of qubits. So that's a proposal for a new type of EDSR qubit that would be useful. If you had these types of much longer range couplings, you could then think about doing types of architectures that is sort of pictured here. I guess this is not much more than a schematic, but the idea is that you have modules of closely packed qubits, and they could be coupled with the types of mechanisms we've been thinking about, but then have much longer range couplings to another module. And in this way, you could build up your architecture, building it up module by module, with much more reasonable pitch of gates and possibility of control. And this seems like a natural fit for quantum error correction architectures. So this is not my picture, this is a picture by Lieven van der Sijpen. So I guess, what have we seen in this talk? I've shown you at the beginning a bit of Feynman's dream, the idea of being able to fabricate devices atom by atom and build up the types of devices that you would like. We saw that atomically precise fabrication. We saw things like the fidelities for single qubit gates being well above 99%, and the fast and accurate readout times that we can have in these devices. You saw the way that we could Michelle Simmons and her team can fabricate arrays of quantum dots here with 10 quantum dots and 2 qubit gates. And then we talked about the potential for scale up in these devices. We saw, first of all, a proposal that made reuse of the gates in order to control the qubits, and that's one proposal. But then we also considered other mechanisms that we could consider for scaling up to quantum error correction, including the EDSR type qubit, electron shuttling, and coherent coupling to superconducting resonators. So it's exciting times at the moment in semiconductor quantum computing, and there seem to be quite a few avenues forward to scale up to quantum error correction, but it'll be exciting to see what the future holds. So thank you for your attention.
Any question? Thanks for a very nice talk. So I have a question regarding calibration. So as far as I understand, all these semiconductor-based quantum computers required quite complex calibration before we can use them. So can you say something about what happens with this if we scale, for example, from 100 qubits to 1,000, 10,000? Wouldn't it be feasible to do this calibration?
Yeah, so that's a very good question, and I guess I don't have a full answer for that yet. Yes, so I guess there's a number of things that you would want to calibrate. You know, for example, your Rabi frequencies, exactly the frequencies of each of the qubits that can change over time. So yes, you're absolutely right that you would want to recalibrate these machines. I guess in much the same way you would want to recalibrate a lot of the devices people are thinking about. Yes, it could be quite difficult to do that. But I don't think it's an impossible task to do to calibrate the devices and to calibrate each of your qubits. So yeah, it's an issue, and I think it's probably an issue for everyone.
Thank you.
So, So you showed us some nice fidelity numbers, but we heard the other day that if we're trying to really design error-correcting codes that are best for a specific hardware platform, that's going to depend not just on fidelities, but on a more detailed understanding of what exactly is failing when we have this failure. So can you comment on what the error channels, what the biases potentially on those error channels are for this kind of hardware?
Yeah, I think the general point is right. It's really important to work with the experimentalists to really understand the types of errors that you've got and how they'll affect, that will play into the error correction codes. I guess, there's a number of ways that errors feed into these devices. Through charge noise is one clear way that they do here. So particularly when you're thinking about exchange and qubits which have a charged dipole-like nature, that's one way that it'll definitely feed in. I guess we do have an understanding, I guess, of that. You can characterize the ways that happens, and so this is some of the numbers for these devices where we're characterizing exactly the charge noise and the way that for these devices, and it's some of the lowest for these types of devices. But yeah, it's very important to understand exactly what your sources of noise are physically and how they play into the whole the error correction schemes. Yeah.
Yeah, fantastic. Thank you. The slide's what I wanted to see.
Yeah, thanks.
So regarding the control complexity and also calibration problems, so I was wondering how about the crosstalk problems for the control part. So, and how local is the crosstalk?
Yeah, so this is a really good question, and I guess that's so for a number of reasons and a number of different ways that you could get crosstalk in these devices. So particularly when you've got wires which are so closely spaced and qubits which are so closely spaced, you can certainly have issues of crosstalk. A lot of the time here we're applying magnetic fields which apply to a large number of qubits at once. So there you naturally have that, but I guess I don't have yes, that is an issue. I guess I don't have a specific answer.
Basically, can you control them to be local? I mean, the crosstalk to be local. So within some particular range.
Yes, that's right. So yeah, you can. I mean, you can definitely control could control at least in principle individual qubits. One of the advantages, I guess, of the EDSR type qubits is that would be through voltage gates rather than the magnetic field, and that would be much more local.
So a question about STM fabrication techniques. I'm over here.
Yeah, sorry.
Okay.
Yeah.
Well, if you hang around in Delft long enough, you hear people complain about E-beam lithography.
Yeah.
And it's not like commercial photolithography where you project light through a mask and you hit the whole area of the chip you want to do lithography on all at once.
Mm-hmm.
You're rastering a tip over a sample, so
Yep.
every feature you want to define takes more time. Is STM, does it have that same feature, and do you see this as an obstacle to getting the huge device sizes that we crave in QEC?
So I guess I'm not an experimentalist, but from what I've seen, at least that's not going to be an issue for quite a while. So they are able to fabricate, really quite well, quite large devices. So yes, eventually that might be an issue, but I guess there's a lot of time before I think it becomes an issue.
Per site, how closely can you control the number of donor atoms? Like
Yeah.
if you
So
can
so
do
this is
zero.
true. So we can't can't necessarily precisely control that, but there's efforts going on to control that more and more precisely. So yeah, I guess at the moment I guess it's not deterministic exactly exactly how many donors you get per site, but there's definitely work going to make that much more deterministic.
Thanks.
So I'm wondering if you have an advice for people working on theory. Do you think there is anything in your hardware that is underexploited in error correction, or that we could exploit, we should exploit?
Yeah. So that's a really good question. So I guess there's a number of different things. I guess one is that when you think about the real devices, like there's going to be a number of different types of qubits and different types of error rates and so on. And so I know that obviously we've got asymmetric noise, but these types of devices are going to have maybe longer range couplings, which are maybe much more faulty, shorter range couplings, different types of qubits. And so, that kind of like, with different types of qubits, different types of noise for each of those. So some work in that direction would be really nice. I think also with these types of devices, there's, things like the nuclear spins. So, it's kind of easier to fabricate some of the qubits and other types of qubits. So, designing codes which can really like take advantage of which qubits are easy to make and make a lot of would be really good.
No more questions? Okay. Let's thank Charles again.